Hello, my students. Today we are going to cover force and acceleration in kinetics part of these courses. As we said, there is kinematics part, there's kinetics part. Then after that, we are going to jump to vibrations if we have time. First, let's go through again a little bit. What are we gonna talk about? What is gonna be the subject and task? This is the kinetics of a particle. We are gonna concentrate right now force and acceleration, then after that work and energy, then this collisions, impulse, blah blah is gonna continue. Kinetics of a particle, what it is a branch of dynamics that deals with the relationship between the change in motion of a body and the forces that causes this change. So kinetics is when we are taking care of the body or mass of the object, we are calling this one is kinetics. If we don't use this particle's body, it means like the mass, it's kinematics. We were finding the acceleration, velocity, and the distances previous parts, so we weren't dealing with the mass of the objects or the particle, so it was geometric aspects. In the Newton's second law, basically we are going to concentrate, and the mass, it reflects the inertia of these forces. What it means, like if we have F is equal to ma, let's say the rate of change of the velocity, right? The rate of change velocity. So the resistance of this change of velocity is coming to mass. So m is a coefficient, is a constant. So we are calling it's this particle's inertia. That's why when we say inertial force, it's coming from this acceleration multiplied by some other stuff. Newton's second law can be verified experimentally by applying a known unbalanced force F to a particle and then measuring the acceleration A. So we had F is equal to ma and m is equal to f over a, as it's shown in this place. M is a scalar and is constant. It doesn't change with time or like any other unit or quantity. Being constant during any acceleration, m provides is inertia, as I just stated before, is the resistance of the change of the particle's acceleration or velocity, sorry. And if the mass of the particle is m, Newton's second law of motion is stated by F is equal to m multiplied by acceleration. We have, for Newton's law of motion, there are three Newton's law of motion. The first one is if balance, if there is like force in balance, it's gonna be in like if net force is zero, there is either zero acceleration or constant velocity. It's in statics basically. The second law, which is we are concentrated on, if there is like a change of momentum of the particle, that means there is a change of acceleration, or there is an acceleration cause this changing momentum. And the third law is if two objects crash or hit each other or exert a force each other, they are gonna be re-affected. So if you hit one object, the object is pulling you back, so it's gonna be opposite sides. And this is the third law. In here they say if there is like shortly after Newton stated these three laws, he stated also the governing the mutual attraction between any two particles. If there are two particles, very small particles, let's say, it has attraction or repulse each other, and it's stated by in mathematical force is F is equal to capital G m1 multiplied by m2 over r square, where F is the force of attraction between these two particles, G is the universal constant of gravitation, m1 and m2 different objects or particles mass, and r square is the distance between these two particles center. And for ourselves, we are using the weight or the force acting down is mg, as we know from our physics 1 or high school physics. This g is here is universal constant of gravitational and the mass of Earth over the distance between Earth's center to this object, whatever the, for example, us or whatever it is. Okay, so the distance between the Earth's center to the hour is calculated experimentally, and it states 9.81 meter per second square. So we use for in our sake mg, and g is a constant 9.81 meter per second square. If it is feet in imperial constant is 32.2 lbf. The equation of motion, I will just briefly state it here. If we have two different or three different or multiple forces acting on a particle, as here in the blue dot, okay, here the blue part, we need to make it a component, and then we need to find the resultant force. So we need to make a free body diagram and then find the resultant force. If we have the resultant force, we need to make it kinematic diagram, where the acceleration of this particle, where it located the direction. Okay, so free body diagram, all the components of the particles we are gonna state. Then after that we are gonna use our kinematic diagram in order to find the direction of the motion. The acceleration is also zero, so that for this one, like what it means, the total F is equal to 0, then the acceleration is also 0, where in the y direction. In this one, if the F2 in y direction and F1 y direction is gonna be added each other, and then if there is no motion, is just in the horizontal motion, that means these two forces y direction is cancelled each other, and there is no motion, so there is no acceleration in y direction, so it is in static equilibrium. I will just give a break, and I will come back again. In the inertial reference frame, we need to use a reference frame, like where we are located or where the observer is located. It may be moving reference or a static reference, it doesn't matter. But if it moves, it shouldn't have acceleration. If it has acceleration, it's gonna be mass, because we cannot follow what the object, the other object, what we are observing, this object having acceleration. Because if we have the reference frame is moving with an acceleration, the other object having the other acceleration is gonna be a complex task. So we are, to do the reference frame to make the problem easy, not a complex task. So that's why we are choosing the fixed frame or translational in constant velocity. But mostly, as we know, that rectangular coordinates, polar coordinates, normal tangential coordinates, and cylindrical coordinates, all of them we are making fixed. When we pass the other, this one, yes. When we define equation of motion for a system, right? Since now we concentrate one particle. What if it is a system? What if it's a system? Like if there is a control volume and there are too many particles on it, and then they affect, they attract each other or reimpulse each other, or if they have external forces like electrical, magnetic, or contact forces, gravitational forces, what happens? How we are gonna calculate? We are gonna define, we are gonna say, okay, capital Fi is gonna be external forces, and small fi is gonna be an internal forces. This addition is gonna give us the each particle's mass multiplied by each particle's acceleration. So the system's motion, equation of motion, is stated by the total forces, internal, external, is equal to mass of each particles multiplied by acceleration of each particles. But the internal forces, we know that if the system is closed system, so the internal forces each other is opposite, so it's cancelled each other. All the internal forces is gone, only bringing the external forces. So and external forces, we can state that the mass of the center of mass acting the mass on it, giving us the external forces. So we can write it MAG is equal to MI AI, or total of F is equal to MAG, which is center of mass. And usually we are using this one, but in the equation of a motion to a body, we are considering as a single particle, and we just do center of the mass of this single particle, and then we just added each other mi to total mi, and then we find the mass of this system, then finding the center of mass, this acceleration, we are calculating this acceleration, and then when we multiply it, we find the total force acting of this body or system. We are gonna see these examples. I'm not gonna solve here because it's gonna be a complex test for me, and then it's gonna be taking too much time. As usual, I'm gonna use my tablet to solve these questions, and I will submit to upload to a YouTube channel. Then you guys can follow that. Again, this example too. We are gonna have 7 or 6 examples, and then I'm gonna upload it into YouTube, and then with the solution, then we can you guys can follow it. Okay. My recommendation: first, listen till here, then go to YouTube and then watch this 2 examples, then come back and then continue the rest of the. So when we use equation of motion, we need to have, as we stated, a reference frame. First reference frame is common is rectangular coordinates. In rectangular coordinates, as we know, there is x, y, z, and with respect to this one, there is an unit vectors, which is I, j, k. So if we know that f, total F is equal to M multiplied by mass multiplied by acceleration, and force and acceleration in the vector form, if we take it out the components, we can state that the total force in x direction plus total force of y direction plus total force on z direction is equal to mass, the constant mass of all these acceleration components, which is x direction, y direction, and z direction acceleration. So we know that I, an x direction component, cannot mix with any other component. So fx, total fx is gonna be equal to m multiplied by ax. Total fy is gonna be equal to m multiplied ai, ay, and fz, total of fz is equal to mass multiplied by z direction acceleration. We know that acceleration and force is gonna be in the vector form. If we want to take the magnitude of them, we need to square of each components and then take the square at each other and then take the square root of it, and we will find acceleration's magnitude or force magnitude if it is necessary. I will just pass by first this one, then after that I will bring back, because I will go through the first the other component, other coordinates. Then after that I will come back and then I will explain you the way how we are gonna approach to solve all these problems. So if we know how can we solve the rectangular coordinates, if the motion is in straight line or in y direction or x direction or xy direction, and a straight like linear line, is gonna be solved easily in rectangular coordinates. But if it is curvilinear motion, like in this roller coaster, or in this blue line, or the curve of the road, whatever it is. So if there is curve, we need to use tangential, normal, and here there is one more term coming, binormal direction. It is the third direction, as we see in tangential direction here and normal direction here, and the other side is gonna be upside or the outside. For example, in the roller coaster is gonna be a normal direction, right, in the bottom side, and a tangential direction, and then if we go out of the picture, it's gonna be the binormal direction. This binormal direction in the curvilinear system is gonna be 0. The total force, the force can be exerted in the x and y direction, but the net force is gonna be 0. So we are gonna say FB is gonna be 0, normal force is gonna be MAN, and the tangential is gonna be MAT, the tangential acceleration. As here, the same thing as we saw here in the kinematics part, right? And we have the last one. Last one is the cylindrical coordinates. Cylindrical coordinates, we have 3 dimension, r, theta, and z direction. If it is polar dimension, polar coordinates is gonna be just r theta, and z direction is gonna be 0. So in the coordinate systems is that much, and I will go back and I will continue. So if we want to solve equation of motion in any coordinates, I just write here rectangular coordinates, but in any coordinates we should follow certain rules. We need to select, first of all, inertial coordinate system. Which coordinate system we are gonna use? Rectangular, curvilinear, polar, or cylindrical coordinates. Okay, we need to decide which coordinate system we are gonna use. First, we need to select it. After we select it, we are gonna use free body diagram. We need to use free body diagram to take in this picture for simplification. Okay, we just need to write it down, all the components or everything we are gonna write it down, and then we just taking these pictures, like complex pictures, to technical drawing, to simplify and to see all the forces affecting on a particle. After that, we need to sense which side of this system is gonna go through. So it's gonna go in down or plus. Let's give an example. Okay, let's try to understand first the question, and we will solve. So we have a one block. This guy is pulling by the 100 Newton force on the right side. By the time the spring has a length of 0.3 meter and is pulled by right side, and then the spring is stretched. S is given is 0.4 meter, and it's asking like what's the end of this motion. Okay, from our trigonometric knowledge, we know that if we have 3, 4, and this is 5, right? 3, 4, 5 triangles. So therefore, that one, without any process, we know that is 0.5 meter by the common knowledge. Then we are gonna see that how much the spring is stretched, because in natural part the spring is 0.3 meter, but when it's the right side, when it's stretched, is 0.5. So it's 0.5 minus 0.3. So the spring is stretched by 0.2 meter. And we know the stiffness constant is 200 Newton per meter. Then we can calculate the spring force is, we know that it is K multiplied by N, K multiplied by X. So it is Kx, which is 200 multiplied by 0.2, which is 40 Newton is the spring force. Let's draw right now the free body diagram. Let's see, this is that guy, okay, that block in position B, let's say. Still there is force, which is 100 Newton meter, and we start to have the spring force, which is on the diagonal part, in the downside, because it's pulling, which is this one, 40 Newton. This is 100 Newton, right? And due to the mass of this block, there's gonna be a normal force acting on it, which is, if there is mg, this is mg. So if there is a friction, we need to multiply by nu, then it's gonna be on the if the motion is on the right hand side, see, which seems like steel is going on the right side, then we will have a friction force over here by nu mg, which is, or n, which is the normal force on acting on this one. So this is our free body diagram. Alright. Alright, in this question, the block A is going on the right side, is given, and as common sense we can see, if the rope is going to the right side, so it's gonna lose, so block B is gonna go to downside. Alright, let's draw our free body diagram. In this question we just need to get used to the free body diagram, that's why it's given this example. So this is block A. We know that there's a tension which is pulling this block A on the right side, which is, we can say the tension of this rope is T, then we know that due to the mg, which is the weight of this block is m, the base of this block is m, and the weight is m multiplied by the gravitational acceleration. So the normal force is the reverse of mg, so it's going to be minus mg outside. And we have a negative side is nu, which is the friction coefficient, and normal force nu n is gonna give us the friction force, which is like try to stop with a given force. For block B, so it's a cylindrical shape. This is block B, and we don't have anything. We just have, again, this block is, the mass is m, so it's gonna be mg. There is no frictional force, but there is an the rope pulling it upside, so there's a tension. So this tension is T on the right side and T on the left side, because T is the here, as we see, T is coming over here, and then there is one T, there's another T, which is when it passes from this poly, it's gonna be the same thing. When it's come to this poly, it's gonna be the same thing. But there are two T is carrying out this block B. That's why we need to draw this T. So 2T basically is mg, 2T is basically mg. That means T is equal to 1 over 2 mg. And then we know that T is nu n. T is equal to nu n, he said. N is mg. T is 1 over 2 mg, which is, this is nu mg. These mg's cancel, so our nu, the friction force, is here 0.5. But we found that the coefficient of this surface is 0.5 and is constant, is coefficient, so there is no unit, so we just need to write 0. That's it. As in physics, we sense that the motion where it goes. Then after that, after we sense the direction, we are gonna make it the kinematic drawing. Okay. So free body diagram, then kinematic diagram. We are gonna write it down our kinematic diagram. As here is stated, the acceleration may be represented as the ma vector on the kinematic diagram. So after we sense, we are gonna draw our kinematic diagram. After kinematic diagram, identify the unknown in the problem. So what it is asking, the velocity, acceleration, whatever. We just need to identify it. Then after that, we are gonna write it down our equation of motion. So free body diagram, all the forces, we are gonna bring it. So, and in x direction, y direction, z direction, all of them, we are gonna make it into the components. So we just writing down the equation of motion, like total fx plus total fyj plus total fzk is equal to max plus mayj plus mazk. This is the equation of motion. And plus this one, if there is a spring in this system, we need to add it as this spring constant spring force equation, which is Fs is equal to Ks. Instead of Ma, we just gonna write it Ks. As here the distance between the unstrenged to the strange length, so difference between the difference is before and after force applied. So delta S is gonna be our distance, and K is the stiffness of the spring, which is gonna given. And friction, if there is a rough surface, we need to use F is equal to F friction is equal to nu K multiplied by N. N is the normal force acting on the body, multiplied by nu K is the friction constant coefficient. Friction coefficient is given also in the examples or the problem. When we stated equation of motion and this spring, if there is spring or friction, or if we stated all these frames and blah blah, and then we solve our questions. After we solve from total F is equal to Ma, the kinetic part of it, then we will go back our kinematics side in order to find the velocity, the position, right? Because we know the acceleration. So we have three cases. If acceleration is a function of time, we just need to use A is equal to dv dt and V is equal to ds dt, taking the integrals, and then we will find the velocity and the position of the particle. If acceleration is a function of displacement, then we know that there is a formula A ds V dv. So we are going to take again integral, then we will find a acceleration as a function of position. If acceleration is constant, then we know that we have a formula V is equal to V0 at, or S is equal to S0 plus V0t plus 1 over 2 a t square. V square is equal to V0 square plus 2a delta S to determine the velocity or position of the particle if the acceleration is constant. So after all this one, we just need to define our acceleration, position, the velocity of everything, and equation of motion. If the solution for an unknown vector component yields a negative scalar, it indicates that the component acts in the opposite direction. That's simple. This is the way of how we are gonna approach the questions. So this kinematics parts, the first kinematics parts of the class lecture is gonna be done here, and I am gonna, as I said, I'm gonna solve all these examples. In this question, we have an inclined surface and a motor winds in the cable with a constant acceleration such that the 20 kilogram crate moves a distance as here 6 meter in 3 seconds, and it starts from rest, so there is no velocity at the beginning, then it comes this 6 meter distance in 3 seconds, and we are gonna find the tension on the cable, right? And it's given the coefficient, the kinetic coefficient of this surface is 0.3. What is our first step is we need to, the first one is establish a coordinate system. First of all, we need to establish a coordinate system. So if we have an inclined surface, then we can say, okay, in my y is like tilted in this surface and my x in here, but I know that the horizontal surface is like that guy is horizontal and we have 30-degree tilted. degree tilted. But my new coordinate system just being easier. So x in that direction and y in that direction, which is 30-degree tilted on the clockwise. So okay, then let's go to second one, which is second step of us is draw a free body diagram. So we are gonna draw, just to be a convenient, draw a free body diagram. What we have an inclined surface, let's say, okay, again, and I have an grade over here, and I have tension here as a force, right, on the cable, and I have that one, we have here a friction force, which is mu and the normal force, and we need to calculate the normal force acting on this surface in this direction, because we know that the gravitational force in that mg. So there is an angle differences. So I need to find the normal which is acting on this surface with a like mg something, right? And I need to calculate the friction force acting on this body. All right, after we draw the free body diagram, we need to go to third step, use kinematics. Kinematics. Use kinematics, not kinetics right now. We are going to use kinematics equation to determine acceleration. So we need to define our geometric terms, right? Okay, let me pass by here. We know that we have a formula S is equal to V0t plus 1 over 2 a t square is given us the distance, right? V0t plus, if there is no S0, so we are gonna consider S0 is 0, and we know that V0 it starting from the rest, so our initial velocity is 0, is gone 0. So just plug the other terms. 6 is the distance passing by s minus s0 is 6 meters. 1 over 2 a, which is we need to find, t is 3 seconds, so 3 seconds square, right? So I can find our acceleration is 6 multiplied to 12 over 9, which is 1.33 meter per second square. So we already find the third step, which is acceleration. Okay, the final step, which is 4. When we come to 4, we need to apply the equation of motion. So right now we come to kinetics part, and we are going to apply the equation of motion. What it is, let's go to again blue. Total force is equal to T minus nu n, right, from the first free body diagram. Then we have also, let's we
see here we have this mg, but from the force and from the weight we have also the components on the left hand side, which is in the minus direction, minus mg sine 30, because the degree is 30, is our equation of motion, right? As you see here, mg between these guys is 30. When we multiply it, sine 30 is gonna be on the down, and if we multiply sine 30 is gonna be on minus direction, in the minus x direction. So we consider minus x direction. All right. So we set up our equation of motion. Let's continue by applying all these terms in order to find our t values. So t minus nu, we know that is given 0.3 n, which is mg, minus the mg is this, n is also this, we need to multiply by mg cosine 30. So just start with n. Oh, that's right. Mg cosine theta. Let me write n in order to not to make it. So mg is 20 because the create is 20 m, and we need to multiply by g, and we need to multiply by sine 30 as here. Sine 30. Which is equal to the force, the total force. What is it? It is this grade, which is 20 multiplied by ma. What is a? 1.33. We already calculated, right? Ma is giving us the total force acted on it. So maybe we can divide it into components, which is my, which is also n. So this one is x, right? So this is one a, n minus mg cosine 30. Mg cosine 30 is giving us what? What is in y direction force? Is 0, right? Because in equilibrium, it's not moving in the y direction. So we can say n is equal to mg cosine 30, which is n is 20g cosine 30. Okay, when we know these two, I can bring this n into here, and I can calculate t values. So and like, let's calculate here. If I calculated n, which is g is 9.81 multiplied by 20 multiplied by cosine 30, it's gonna give us 169.9 Newton. So if I bring this n here, so t is equal to 20 multiplied by 1.33 plus 20g sine 30 and plus 0.3 multiplied by n, which is 169.9, is gonna give us tension. Just when you calculate it, you will see it's gonna be 176. So we find the tension on the rope with given motion.